Hey fellow nerds, welcome to the first video of our analog circuit series. Today we will discuss some basic concepts required for analog circuits. We will be covering resistors and capacitors, basic circuit laws, introduction to semiconductor physics, PN junction as a diode, Zener diode, and types of characteristics. Let us start with a resistor of resistance R. We all know what a resistor does in a circuit. It limits the flow of current. Let us apply a DC voltage across the resistance. Positive terminal of the cell is over here, its negative terminal is here. So this end of the resistor will get positive polarity and this end will get negative polarity. And the direction of current will be anti-clockwise. Here the applied voltage V, current I and the resistance R are related by the equation V is equal to IR. We can actually compare it with Newton's second law, F equals ma. When a force is exerted on a body, it tries to have an acceleration and the mass tries to oppose it. When a voltage is applied, current has the tendency to flow, but resistance will try to stop it. So resistance limits the current flow in a circuit. Another thing it does is, it converts electrical energy into heat energy. The energy dissipated is given by the expression Vi or V square by R or I square R. Let us now take another resistor of the same resistance R. This time I want to apply an AC voltage. Here also the relation between applied voltage V, current I and R can be written as V equals IR. The only difference is V is alternating. So for example, if you take V is equal to V naught sine omega t, then I is going to be V naught divided by R sine omega t. So current is also going to be alternating. But my question is, does anything happen to the resistance of the resistor because the applied voltage is alternating? If I alter omega, which is the frequency of my applied voltage, will it change resistance? The answer is no. Resistance does not depend on the frequency of the input. So if I draw a graph between the resistance of the resistor and the frequency of the input voltage, it will look like this. It is a straight horizontal line because R does not depend on omega. You can call this the frequency response of the resistor. Let us now take a capacitor of capacitance C. I want to apply a DC voltage to it. Applied voltage is V. I have taken the current to be I and the capacitance is C. Now, you know a capacitor is made by two conducting plates that are not touching each other. They are placed at a small distance from each other. But my question is, if they are not touching, how can there be a current in this circuit? Well, let me show you what happens. Both the plates of the capacitor are conducting, which means they have lots of free electrons in them. So when you apply the voltage, electrons from this plate will be attracted by the positive terminal of the cell and then they will be pushed towards the other plate of the capacitor by the negative terminal of the cell. In simple words, what the cell or the power source does is it takes all the free electrons from this plate of the capacitor and deposits them on this plate of the capacitor. Since electrons are flowing in this direction, the current will be in the opposite direction. But this current has a problem, right? How long can it sustain? In some time, all the electrons from this plate will go to the other plate and the current will stop. We can show it like this. Initially, at t equal to 0, the electrons have just started to flow, so the current I is really high. At t equal to infinity, which means after a long time, when the steady condition has been achieved, the power source has already taken as much electrons it can from this plate to the other plate. Since this one lost a lot of electrons, it is now positively charged. And since this one got a lot of electrons, it is now negatively charged. Now, the power source is not strong enough to take any more electrons, so the current has stopped. I is equal to 0. We say the capacitor is fully charged. Let us show the variation of current with time using a graph. Current decreases exponentially. When the current has become 0, we say the capacitor is fully charged. The charge stored in the capacitor Q is given by the product of C and applied voltage V. Another thing you can see here is there is a clear separation of charge. This plate has positive charge, this plate has negative charge, and they are separated by a distance, which means an electric field will be developed from the positive side to the negative side. Let us now try to find an expression for the current flowing in the circuit. We know current is given by dq by dt, rate of flow of charge. Here q is CV, so we can write d by dt of CV. C is the capacitance of the capacitor. It is A epsilon naught by D. It depends on the area of the plate, the medium between the plates, and the distance between the plates. It does not change with time. So we can take C out of the differentiation. It is C d by dt of V. So we can write I is C dV by dt. Let's compare this equation also with F equals ma. When a force is applied, the body tends to have an acceleration and mass opposes it. Here, force is analogous to the current, acceleration is analogous to the rate of change of voltage, and mass is capacitance. So we can say capacitor resists the change in voltage. Now, in this case, we have applied a DC voltage across our capacitor. So dV by dt here is 0. That means I is 0, which makes sense because we already saw that here. The capacitor just gets charged and the current becomes 0. Now, between the plates of the capacitor, an electric field is developed. So we can say the capacitor stores energy in the electric field. Energy stored in the capacitor is given by the expressions half CV square or half QV or Q square divided by 2C. Now, let us take the same capacitor with capacitance C and apply AC voltage to it. Here also the applied voltage V, the current I and the capacitance C can be related by the equation I is equal to C dV by dt. Here the applied voltage is alternating. So as an example, let us take V to be V naught sine omega t. Then I will be C dV by dt, that is C multiplied by derivative of V naught sine omega t is V naught omega cos omega t. This obviously is not equal to 0. Instead, it is an alternating current. Here we have sine omega t, here we have cos omega t, which means the current is leading the voltage by 90 degree. If we plot both of these, this is how it will look like. The first thing we can conclude from here is that the capacitor blocks DC but it passes AC. Now let me do something. We have V taken as V naught sine omega t. So V can be written as V naught with a phase 0 degree. I is C V naught omega cos omega t. So I can write it like this. I is equal to C V naught omega. Since it is cos omega t, the phase difference is 90 degree. Or to show the 90 degree phase difference, I can just write I is equal to J C V naught omega. J shows that there is a 90 degree phase difference. In the case of a resistor, we wrote V is equal to IR. Then R will be V by I. Let us find an equivalent property of capacitor here. V by I will be V naught divided by J C V naught omega. V naught and V naught gets cancelled. We get this is 1 by J C omega. So V by I is 1 by J C omega. It is the impedance of a capacitor. Let's write it down. Phase difference between I and V is 90 degree. So the impedance of the capacitor is 1 by J omega C. If you simply take the magnitude of 1 by J omega C, we get 1 by omega C. That is called the capacitive reactance. We denote it using XC. Capacitive reactance is analogous to resistance of a resistor. Obviously, you can see there is an omega in the expression for capacitive reactance. So, unlike a resistor whose resistance does not depend on omega, which is the frequency of the input voltage, capacitive reactance is inversely proportional to omega. So, if we draw the frequency response of a capacitor, this is how it will look like. Let us now discuss some basic circuit laws starting with Ohm's law. According to Ohm's law, voltage across a resistor is directly proportional to the current flowing through it. V is proportional to I. Here, the constant of proportionality will be the resistance R. So we can write V is equal to IR. If we plot the relation between V and I on a graph, this is how it will look like. It is a straight line with constant slope, and the slope will give you the resistance of the resistor. The next law we have is Kirchhoff's current law. According to this, the algebraic sum of all the current entering a node is 0. Or we can say the total current entering the node equals to the total current leaving the node. If you take the summation of all the current going into the node, it will be equal to the summation of all the current going out. Let's take an example. Consider the node over here. This is 2 ampere, this is 1 ampere, and this is I. We have to find the value of I. 2 ampere is coming into the node, I is coming into the node, but 1 ampere is going out. So we can write 2 plus I should be equal to 1, which means I is minus 1 ampere. We got negative 1. That means the magnitude of I is 1 ampere, but the direction of I is not this. It is actually going out of the node. Now let's take Kirchhoff's voltage law. According to this, algebraic sum of potential difference around any closed network is 0. Or we can say in a closed loop, summation of all the potential differences will be equal to 0. Let's take an example. Applied voltage is 1.5 volt. We have a 1 ohm resistor and an unknown resistor. Current flowing through the loop is 1 ampere. Positive terminal of the cell is connected to this end of the resistor, so it will have positive polarity here and negative here. For the other resistor, this end is connected to the negative terminal of the cell, so it will have negative polarity here, positive polarity here. Another way in which you can check the polarity of the resistor is by looking at the direction of current through it. For example, in the resistance R, current is flowing in this direction. Current always flows from the positive polarity to the negative polarity. So we should have positive polarity here and negative here. Similarly, for the 1 ohm resistor, current is flowing from here to here. So here we should have positive polarity, here we should have negative polarity. Now we have to take the summation of all the potential differences. Let us start from here and go clockwise. First, I have a 1.5 volt. So I'll write 1.5. As I go on, I can see there is a resistor. It has some potential across it. According to Ohm's law, that will be IR. I here is 1 ampere. R is also 1. So V is 1 volt. But the polarity is opposite. The cell had minus to plus. This has plus to minus. So I have to write minus 1 volt. The same way, I have another resistor. Across it, there will be some potential drop. Using Ohm's law, it will be V is equal to IR. I is 1, R is unknown. Again, the polarity is opposite. So minus R multiplied by 1. This is equal to 0 according to Kirchhoff's voltage law. From here, I can easily write R is equal to 0.5 ohm. I know all these are pretty simple, but when it comes to complex circuits, lots of people make very basic mistakes like this. So I thought it is better to go through the basics first and then get into the actual circuits. Let us move on and have an introduction to semiconductor physics. We will start by taking the atomic structure of silicon. A silicon atom has 14 electrons. 2 of them are in the lowest energy level, 8 of them are in the second lowest energy level, and 4 of them in the outermost energy level. A silicon atom has 14 electrons in it, but all 14 of them do not have the same energy level. 2 of them are in the innermost shell and they have the least energy. 8 of them are in the second shell and 4 are in the outermost shell. The 4 electrons in the outermost shell have the highest energy. The outermost shell is called valence shell and these electrons are called valence electrons. All these valence electrons are bound to the atom. But if they get enough energy, they'll be able to break free and move around freely. This will make them available for conduction of electricity. In a single atom, all the valence electrons will have the same energy. But when a semiconductor wafer is made of a large number of atoms, these valence electrons will be influenced by their neighboring atoms. The most important consequence of this is that the valence electrons may occupy slightly different energy levels. To visualize this, let us take the energy level on the y-axis of a graph. The valence electrons are now taking slightly different energy levels. Let us show them in the graph. This electron has this much energy, this one has this much energy, and this one has this much. Even though they are taking different energy levels, there is a maximum and minimum value of energy they can take. Let us mark it. We can define this as the band of energy that the valence electrons can take. We call this the valence band. Now, we know if the valence electrons get enough energy, they will get out of the influence of the atom and they will be able to conduct electricity. So obviously the electrons that are available for conduction will have much more energy than the valence ones. Let us show them also in the graph. Even conduction electrons have a range of energy that they can take. Let us mark it on the graph. This is the band of energy that the conduction electrons can have. We call it the conduction band. You can see there is a gap between the valence band and the conduction band. There are no electrons there. That means none of the valence electrons or the conduction electrons can have energy levels that are between these two values. We call it the energy gap. This representation of energy levels of the electrons in a material is what we call energy band diagram. For metals, it will look like this. Here the conduction band and the valence band are overlapping each other. What it means is that there can be electrons in the conduction band and in the valence band who have the same energy. So in metals, it is very easy for the valence electrons to gain some energy and go to the conduction band and start conducting. In insulators, this is how it will look like. Here the energy gap between the conduction band and valence band is too high that it's very difficult for the valence electrons to gain that much energy and go to the conduction band. That is why insulators are bad conductors of electricity and metals are very good conductors of electricity. In energy band diagram for semiconductors, the conduction band will not overlap the valence band, but the energy gap is relatively small. Because of this, the electrons from the valence band will be able to jump to the conduction band easily if they get enough energy. Using this idea, let us write down a definition for semiconductors. They are the materials with electrical conductivity between that of conductors and insulators. Let us also define conduction band, valence band, and energy gap. Valence band includes the lower energy levels where the electrons are bound to the atoms. Conduction band has the higher energy levels where the electrons can move freely. Energy gap is the energy difference between the valence band and conduction band. For silicon, it is approximately 1.1 electron volt, and for germanium, it is approximately 0.7 electron volt. We know for a semiconductor, there is some energy gap, though it is very small. So the valence electrons need some energy so that they can jump to the conduction band. So we can say with no external energy, all the valence electrons will reside in the valence band and the conduction band will be empty. Let us now take the energy band diagram of a semiconductor. Here is the highest energy level in the valence band. Let's call it EV. Here we have the lowest energy level in the conduction band. Let's call it EC. We know energy gap is the energy difference between the conduction band and valence band. So we can write EG is equal to EC minus EV. From what is shown over here, there are so many electrons in the valence band with different energy levels. Let us assume that some of them got some energy and they were able to go to the conduction band. According to this, 3 electrons were able to get enough energy to go to the conduction band. But while they do this, they actually leave some gap behind in the valence band. We call them the holes. Now, the 3 electrons are in the conduction band and they are available for conduction. Let us take the semiconductor represented by this energy band diagram. I have shown the 3 electrons in the conduction band and the 3 holes in the valence band. Now, I am going to apply a voltage source across this. The positive terminal is connected to this end and the negative terminal is connected to this end. So, this end of the semiconductor will get positive polarity and this one will get negative polarity. From positive to negative, an electric field will be developed. We know electrons are charged particles. What does an electric field do to a charged particle? It will exert a force on it. The force will be equal to charge on the particle minus E multiplied by the electric field E. So the force is in the opposite direction of the electric field. So the electric field will exert a force on the electrons that will make them move towards the right. This gives rise to a current and we call it the electron current. Electron current is the flow of negatively charged free electrons in the conduction band of a semiconductor. Why do we call it electron current? To understand that, let us see what happens to the holes that are in the valence band. When this electron came to the conduction band, it left a hole here. Now, another electron in the valence band itself can actually jump into this hole, leaving another hole over here. Similarly, maybe this one can go over here, and maybe this one can go here. Now, instead of saying the electron went from here to here, we could say the hole went from here to here. Effectively, we can think of holes as a positively charged particle. This will help us differentiate whatever is happening in the conduction band and whatever is happening in the valence band. Let's go back to this circuit over here and see what happens to the holes. Positive terminal is connected to this end, so we have positive polarity here. Negative terminal is connected to this end, so we have negative polarity here. We have considered holes to be positively charged particles. So the electric field is going to exert a force that is equal to plus E. Here the force exerted will be in the direction of the electric field, that is towards the left. So the holes will move towards the left. This will also give rise to a current. We can call it the hole current. Hole current is the movement of the holes effectively acting as positively charged carriers. The most important thing you have to understand here is electron current is due to the electrons in the conduction band. Hole current is due to the electrons in the valence band. We know it is easier for the conduction electrons to move, but it is difficult for the valence electrons because they are bound to the atoms. So motion of a valence electron depends on how easily it can release from its atom and get trapped by another atom. Or if we talk in terms of holes, we can say it depends on how easily it can get released from an atom and get trapped by another one. We can say that holes are slower than electrons because their movement depends on the trap and release of electrons. When we say electrons here, we mean the electrons in the conduction band. When we say electrons here, we mean the electrons in the valence band. Holes are slower than the conduction electrons because their movement depends on the trap and release of valence electrons. Let's go back to the circuit again. Electrons are moving to the right side, that makes a current towards the left side. Holes are moving to the left side, since they are positive, they give rise to a current towards the left side. So we can write the total current is IE plus IH, that is the sum of electron current and hole current. Now, the simplest or pure form of semiconductors where we haven't done any modifications ourselves are called intrinsic semiconductors. If we draw the energy band diagram of an intrinsic semiconductor at absolute zero temperature, this is how it will look like. There are no electrons in the conduction band. All the electrons are in the valence band. That is because the temperature is absolute zero, so none of the electrons were able to get any heat energy, so they could go to the conduction band. Let's draw the energy band diagram of the same semiconductor at room temperature. A few of the electrons got enough energy and they went to the conduction band. In the case of intrinsic semiconductors, however many electrons have went into the conduction band, those many holes will be created in the valence band. If we take n to be the number of electrons per centimeter cube and p to be the number of holes per centimeter cube, for an intrinsic semiconductor, these will be equal. Let us take them to be Ni. Ni is the number of carriers per centimeter cube for an intrinsic semiconductor, or we can call it the intrinsic carrier concentration. Since P and N are equal and they are equal to Ni, If we take the product of P and N, we get Ni squared. Let's take an example. For intrinsic silicon, the number of atoms per centimeter cube is 5 into 10 raised to 22, and number of free electrons is 10 raised to 10 per centimeter cube. This is a very low number and it is true for all the intrinsic semiconductors. So we can conclude intrinsic semiconductor is a poor conductor. Now we have to do something to the intrinsic semiconductors to increase their conductivity. Once we do that, we call them the extrinsic semiconductor. This is how we do it. Conductivity of a semiconductor can be improved by adding impurities to it. This method is called doping, and the impurities we are adding to the intrinsic semiconductor are called dopants. There are two types of impurities we can add, depending on which we have two types of extrinsic semiconductors. The first type is N-type semiconductors. Here the dopants are pentavalent atoms like arsenic, antimony, and bismuth. To understand what happens when we add dopants, let us take the crystal structure of intrinsic silicon. Valency of silicon is 4, so one atom can make 4 bonds with other atoms. You can also see some of these electrons have come out of the bonds, leaving holes back. Now, when we add impurities to this, some of these atoms will be replaced by those atoms. As an example, let us assume this atom is replaced by an impurity atom. Impurities are pentavalent. That means they have 5 electrons in their valence shell. 4 of them will be used to make 4 bonds with the neighboring atoms, just like the silicon atom did, but the 5th one will be donated for conduction. Like this, however many impurity atoms you have added, those many extra electrons will be now available for conduction. This way, we have increased the conductivity of the semiconductor. Since these atoms donate an electron, they are called donors. Let's take Nd to be the number of donor atoms. Then the number of new electrons added will also be Nd because each atom is giving out one electron. Now, when we add impurities, we make sure that the number of atoms added are very much greater than the intrinsic carrier concentration. So that when we take the total number of electrons, which is Ni plus Nd, this is approximately equal to Nd itself because Ni is very much smaller than Nd. But what will be the total number of holes? Total number of holes is still going to be Ni because number of holes increase only when the electron goes from the valence band to the conduction band. Since that doesn't happen any more than it has already happened, total number of holes is still going to be Ni, and Ni, as we saw, is very much less than Nd. So we can write the concentration of electrons is going to be very much higher than the concentration of holes. Therefore, in N-type semiconductors, electrons are the majority carriers and holes are the minority carriers. The next type of extrinsic semiconductor is the P-type. Here the dopants are trivalent atoms like aluminum, boron, and gallium. Let us take the crystal structure of a semiconductor again. When we add trivalent impurities, some of these atoms will be replaced by them. Since these atoms are trivalent, they only have 3 electrons in their valence shell. Using them, they will be able to make 3 bonds with the neighboring atoms. For the 4th bond, the semiconductor atom will be able to give 1 electron, but the impurity will not be able to do its part. Because of that, we have an extra hole over here. So, when a trivalent impurity is added into a semiconductor, we get an extra hole. If Na is the number of acceptor atoms we have added to the semiconductor, then the number of new holes added will also be equal to Na because every atom is giving one hole. While doping, we make sure that Na is very much greater than Ni, which is the intrinsic carrier concentration. So that when we take the total number of holes, which is Na plus Ni, since Ni is very small, this will be approximately equal to Na itself. But the total number of electrons is still going to be Ni, the intrinsic carrier concentration, and it is very much less than Na. Therefore, in P-type semiconductors, holes are the majority carriers and electrons are the minority carriers. Let me conclude what we learned. To increase the conductivity of our semiconductor, We add impurity atoms because they have extra electrons and holes. If the impurity atoms have so many electrons and holes, why can't we just directly use them instead of adding them into a semiconductor? Well, the answer to that question is this. For pure impurity materials like phosphorus or boron, they don't have the same crystal structure or properties as a silicon, or basically any other semiconductor material. For a semiconductor to work properly, it should have a stable repeating crystal structure like the one you can see over here. This will help us make the electrons and holes move in a controlled way. The structure is very essential for the working of the semiconductor. Pure impurity metals does not have the same crystal structure, so we cannot directly use them. Let us do something different now. We'll take a semiconductor wafer. On the left side, we will dop it with a trivalent impurity. On the right side, we'll dop it with a pentavalent impurity. Now, we get something like this. Left side is p doped, right side is n doped. So we get extra electrons over here and extra holes over here. Let's have a better visualization. If you take a closer look, you can see I have added the crystal structure as well. What you can see over here are the atoms. Now, obviously there is a concentration gradient. Over here we have so many holes, but here we have very less holes. Over here we have so many electrons, here we have very less electrons. So obviously there will be a flow of the holes and electrons from wherever they are more to wherever they are less. So the holes will start diffusing to the right and the electrons will start diffusing to the left. Holes moving towards the right will create a current in the same direction. Electrons moving towards the left will create a current in the opposite direction. So both currents are towards the right. We call their sum the diffusion current. Electrons diffusing from the n side to the p side will be accepted by the atoms there. When that happens, the atom from the n side that donated the electron will become positively charged, and the atom on the p side that accepts the electron will become negatively charged. Obviously, the electrons and the holes that are closer to the junction will be diffusing first. Therefore, the atoms on the p side and n side that are closer to the junction will start becoming positively charged and negatively charged by donating electrons and accepting them. Then, the junction will begin to look like this. Let us write down what happened. Due to concentration gradient, the electrons from the n side diffuse to the p side and they leave ionized immobile donor atoms on the n side. We are talking about these positively charged ions. Also, holes from the p side diffuse to the n side, leaving ionized immobile acceptor atoms on the p side. We are talking about these negatively charged ions. This gives rise to a current, we call it diffusion current, and the direction of the diffusion current is from the p side to the n side of the semiconductor. Clearly, a layer of positive charges is formed on the n side, and a layer of negative charges is developed on the p side. The two layers were formed when the electrons from the n side were accepted by the atoms in the p side. Which means in this much space we don't have any more holes or electrons that are free for conduction. So we can say the region is depleted of its free charges. Because of this reason, we call it the depletion region. Now, there is a clear separation of charges in the depletion region. We have a layer of positive charge and we have a layer of negative charge. So, from the positive potential to the negative potential, an electric field will be developed. We know electrons are negatively charged particles, and here we have taken holes to be positively charged particles. Force exerted by the electric field on the holes will be plus E multiplied by the electric field. This is in the direction of the electric field. So the electric field will push the holes towards the left. Electrons are negatively charged, so the force exerted by the electric field on the electrons will be minus EE, which is in the opposite direction of the electric field. So the electric field will be pushing the electrons to the right side. Holes going to the left will create a current towards the left. Electrons going towards the right will also create a current towards the left. So these two contribute to a new current. We call it the drift current. And its direction is from the N side to the P side. Let us write this down. An electric field develops from the positive charge towards the negative charge. It forces the electrons from the P side of the junction to move back to the N side and the holes from the N side of the junction to move back to the P side. We call this the drift current and its direction is from N to P. Diffusion current is towards the right, drift current is towards the left. So they are opposing each other. As the diffusion progresses, more holes will go from the P side to the N side and more electrons will go from the N side to the P side. This will make the positive charge over here and the negative charge over here stronger, but that will make the electric field stronger. Then the electric field will be able to push the holes and the electrons back to their original position even better. Because of that, the drift current will increase. In simple words, we can say as the diffusion current increases, the drift current also increases. And since drift current is opposing the diffusion current, at some point they will become equal and the net current will become zero. When this happens, we say the PN junction is in equilibrium. At equilibrium, the diffusion current will be equal to the drift current and net current through the junction becomes zero. Once the equilibrium condition is attained, no more holes or electrons will go to the other side. That means the width of the depletion region becomes a constant, it is not increasing anymore. Let us call it W. There is a layer of positive charge and a layer of negative charge, which means across the depletion region there is a potential drop, let us call it V0, which means a potential difference is developed across the depletion region. This potential difference is what creates the electric field and opposes the flow of charges. So we can say it opposes further flow of the carriers and maintains the equilibrium. This is called the barrier potential. Let us denote it by V0. Now that we know what a PN junction is and how it is formed, let us see how it can function as an electronic device. All you have to do is simply attach metallic contacts on each end of the semiconductor. This is what we call a diode. And what you can see over here is the circuit symbol of a diode. A semiconductor diode can be defined like this. It is a PN junction with metallic contacts provided at the ends for the application of external voltage. Why do we need to apply external voltage? We do it because the equilibrium barrier potential can be altered by applying an external voltage V across the diode. Now, before we go forward, there is an important thing that you have to understand. It is that the external applied voltage will drop mostly across the depletion region because its resistance is high. First of all, why is its resistance high? Because in the depletion region, we don't have any carriers. It opposes the flow of holes from here to here and the electrons from here to here. That means it has high resistance to the current. Now, if we simply take the N part and the P part of the semiconductor, they have loads of carriers in it and they are all free for conduction. That means their conductivity is really high, their resistance is really small. For you to understand this concept better, let's take three resistors. First one is 1 ohm, second one is 98 ohm, third one is again 1 ohm. They are all connected in series. Now I'll apply a potential. This is 100 volt. Potential drop across the 1 ohm resistors will be 1 volt each. But for the 98 ohm resistor, we will get 98 volt. So we can say most of the applied voltage is dropped over the highest resistance. The same thing happens here. We can assume this part to be a resistance of very low resistance. And this one has high resistance. Again, we have a low resistance. So whatever you apply here, most of it will be dropped across the depletion region. Let's take the first case where the applied voltage is opposite to the built-in potential. The built-in potential is negative here and positive here. To oppose that, we apply the external voltage, positive here and negative here. Now, this potential will be dropped across the depletion region. Therefore, the net potential drop across the depletion region will now become V naught minus V. So we can write the effective barrier height is now V naught minus V, which means the holes in the p side and the electrons in the n side now only have to jump a height of V naught minus V, not V naught. Since the effective potential drop across the depletion region decreases, the electric field that is stopping the holes and electrons from going to the other side also becomes weaker. So, more holes and electrons will be able to go from their side to the other side. Because of this reason, the width of the depletion region decreases and it makes easier for the current to flow. It will look like this. Let me remove the atoms in the figure except the ones in the depletion layer so that it is easier for us to visualize what is happening. These are the electrons that just came from the n side, and these are the holes that just came here from the p side. We know electrons are the minority carriers in the p side, and holes are the minority carriers in the n side. So what has actually happened here is that the electrons from the n side cross the depletion region and reach the p side where they are the minority carriers. The same way, holes from the p side cross the depletion region and they reach the n side where they are the minority carriers. Because of this process is called minority carrier injection. We injected the carriers to the sides where they are a minority by applying an external voltage. Now, the just crossed electrons and holes will be concentrated closer to the junction. Or we can say, on each side of the junction boundary, minority carrier concentration increases. Now, simply look at the n side. Over here, we have an abundance of holes. Over here, holes are very less. So there is a concentration gradient. Because of that, the holes will start to flow to the place where their concentration is low. Take a look at the p side. Over here, we have an abundance of electrons. On the other end of the p side, we have very less electrons. So there also we have a concentration gradient. Because of that, the electrons will start moving towards the left. Now, when the carriers move from one point to the other point because of concentration gradient, we call it diffusion. So we can write, due to concentration gradient, the injected electrons will diffuse to the end of the p side and the injected holes will diffuse to the end of the n side. We can visualize it like this. Holes move to the right side, giving rise to a current towards the right. Electrons move to the left side, again giving rise to a current to the right side. So we have a net current towards the right. Let us show in the circuit like this. The magnitude of this current is usually in milliamperes. Here we have connected the positive terminal of the cell to the P side of the semiconductor. The negative terminal of the cell is connected to the N side of the semiconductor. This is called forward bias. Now, by doing so, we are actually helping more carriers cross the junction. By applying a forward bias across a diode, what we are actually doing is decreasing the effective barrier potential, which means now even the carriers with lesser energy will be able to jump to the other side because the height they have to jump has been decreased. Now, if the applied voltage is increased, more number of carriers will have the required energy to cross the junction because we have decreased the energy that is required to cross the junction. Because of this, the current will increase. For practical diodes, the current first increases very slowly, almost negligibly, till the applied voltage crosses a certain value. The minimum voltage we have to apply so that we can see an increase in the current is called the threshold voltage. We'll denote it by Vt. After the threshold voltage, if you keep increasing the applied voltage, the current will increase exponentially. If we show the relation of current and applied voltage on a graph, this is how it will look like. Since the current usually comes in milliamperes, on the y-axis current has been taken in milliamperes. Voltage is taken in volts. I have marked the threshold voltage Vt over here, after which you can see the current is increasing exponentially. Till then, the current is very negligible. Let us again take the PN junction in equilibrium. This is the P side, this is the N side, and V naught is our barrier potential. We know the P side is created by adding trivalent impurities. Because of that, the majority carriers in the P side are the holes, but we know there are still electrons there. The number of electrons on the p side is going to be Ni, which is the intrinsic carrier concentration, and the number of holes is going to be Na, which is the number of acceptor atoms we have added. While doping, we make sure that Na is very much greater than Ni, so the number of holes is very much greater than the number of electrons, which means most of the times we can ignore the existence of electrons. So, to show that there is still electrons in the p side and their number is very less, let me add one electron over here. Similarly, in the n side, we have doped with pentavalent impurities. So, the number of holes here is going to be Ni, which is the intrinsic carrier concentration, and number of electrons will be Nd, which is the number of donor atoms we have added. While doping, we make sure Nd is very much greater than Ni, so the number of electrons is very much greater than the holes. So most of the times we ignore the existence of holes there, but we know there are still holes. To show that there are holes in the n side and they are very less in number, let me add one hole over here. Now that this idea is clear, I want to apply an external voltage. This time I am going to apply the negative potential to the P side and the positive potential to the N side. I have applied an external voltage V. Its negative terminal comes to the P side, positive terminal comes to the N side. Now this potential will be dropped across the depletion region. Here the barrier potential has negative here and positive here. Applied potential also has negative here and positive here. So we can say the applied voltage is in the direction of V0. Because of this, they will get added up. So the effective barrier height will now become V0 plus V. That means the height the electrons and holes have to jump has become even larger. In this case, even lesser electrons and holes will be able to go to each side, which means the width of the depletion layer will increase. Or you could say, since the potential drop across the depletion layer increased, the electric field created by that will also be increased. The direction of electric field is towards left. So on the holes, it will have a force towards the left. On the electrons, it will have a force towards the right. The increased electric field will pull more electrons on the N side away from the junction and more holes on the P side away from the junction. This will widen the region at the junction where there are no more electrons or holes available for conduction. This is what we call depletion region. So the width of the depletion region increases. In simple words, we can say the reverse bias forces more of the mobile carriers out of the depletion region, which causes the depletion region to widen. Now this is going to oppose the flow of electrons from N to P and the holes from P to N. Now we have a very high potential difference across the depletion region, which means we'll have a strong electric field from the positive side to the negative side. Now we know that in the p side, even though very less in number, we still have electrons. And since they are free, they will keep moving in random motion. During their random motion, if at all this electrons somehow reaches near the depletion layer, this is what happens to it. The electric field is towards the right. Electron is negatively charged. Since the electric field is really strong, it will apply a force on the electron that is equal to minus E. Obviously, the force is in the opposite direction of the electric field, that is towards the right. And it is so strong that the electron over here will be swept to the other side. The same thing happens in the N side also. We know that even though the number is really less, there are still holes in the N side. So if the hole reaches somewhere near the depletion region, the strong electric field will exert a force on it. the force will be equal to plus E. Since the electric field is so strong, the force will also be really strong. It will sweep the hole to the other side. Let us write this down. The electric field is directed such that if the electrons on the p side or the holes on the n side in their random motion comes closer to the junction, they will be swept to their majority zone. The electron here is a minority in the p side, but it will go to n side where it is the majority. The hole here is a minority in the n side, but it will go to the p side where it is the majority. Here holes are going to the left side, so we have a current towards the left. Electrons are going to the right side, that also makes a current towards the left. So the net current is towards the left. Let us show it in the circuit like this. Now this current is due to the effect of an electric field, so we call it drift current. And the drift current usually is in microamperes. We saw the diffusion current is in milliamperes, but drift current is in microampere. Drift current is very much lesser than diffusion current. What is the reason for that? The reason is pretty simple. In diffusion current, holes were going from the p side to the n side and electrons were going from the n side to the p side. We have so many holes in the p side and so many electrons in the n side. Because of that, the current is high. But in the case of drift current, electrons are going from the p side to the n side and holes are going from the n side to the p side. We know number of electrons in the p side is very less. Number of holes in the n side is also very less. This is why drift current is much lesser than diffusion current. Drift current is quite low because it is due to the minority carriers. Because of this reason, increasing applied voltage will not have much effect on it. When the negative terminal of the cell is connected to the p side and the positive terminal of the cell is connected to the n side, we call this reverse bias. There is one last thing we have to note here. Under reverse bias, if the applied voltage exceeds a critical value, the PN junction gets destroyed due to overheating, and because of that, the current will increase sharply. That critical voltage is called breakdown voltage. We can denote it by VBR. Now, if we plot the relation between the current and the applied voltage on a graph, this is what we get. When V or the applied voltage is positive, we already saw the current is exponentially increasing after a critical value of voltage, which is the threshold value. Here the diode is in forward bias. In forward bias, the current comes in milliamperes. So on the y-axis, we have taken current in milliamperes. When the applied voltage is negative, the current is almost constant for a long time. That is because the reverse bias current mainly depends on the availability of the carriers. Even if you increase the applied voltage, it is not going to have any effect on it. So we get the constant current until the applied voltage reaches the breakdown voltage VBR, after which the diode gets damaged and the current increases sharply. Now under reverse bias, the current is in microamperes. So on the negative y-axis, we have taken I to be in microamperes. Now let us learn the different ways in which we can model a diode in a circuit. Before that, you need to understand what is a model. A model is a simplified version of something complex. It helps us understand how that thing works without getting lost in all the details. For example, let us say you have a circuit. There is a bulb in the circuit. What the bulb primarily does in the circuit is resist the flow of electricity. So, for the sake of analysis, we can simply change the bulb into a resistor. This will give us a good approximation of how the circuit will function. So, by using models, we can make the circuit analysis easier and more manageable. Now, when it comes to diodes, there are a few ways in which we can model it in a circuit. The first one is the exponential model. We could say this is the most accurate one. Here we take the actual relation between the voltage applied across the diode and the current flowing through it. In forward bias, we consider the current to increase exponentially. In reverse bias, we consider the current to be 0. Because we know in forward bias the current is in milliamperes, in reverse bias it is in microamperes. Compared to milliamperes, this is very low, so we will assume it is 0 in this model. Now, for forward bias, the current ID is given by the expression Is e raised to the power Vd divided by Vt minus 1. We know when a diode is reverse biased, a very small current passes through it. And in the IV graph, we saw this current is almost constant even when we increase the external applied voltage because the current depends on the number of minority carriers available. This small constant current that flows through the diode when it is in reverse bias is called saturation current. We can denote it by Is, and that is what you see over here in this equation. The Vt here is not the threshold voltage, it is thermal voltage. Its value is approximately 26 millivolt. Let's take Vd by Vt. Vt is approximately 26 millivolt, which is a very small number. Since it is in the denominator, the ratio Vd by Vt will be a large number. Therefore, e raised to Vd by Vt will also be a large number. Because of that, we can actually ignore the minus 1. Assume you have 10 raised to 6 minus 1. We can write it is approximately equal to 10 raised to 6 because minus 1 is very small compared to 10 raised to 6. So we can approximate this relation into simply Is e raised to Vd by Vt. Here Is is the saturation current, which is the small current. Now let's see what happens if the applied voltage is negative. In that case, Id will become Is e raised to negative of something. But since Vt is a very small number, Vd by Vt is a very large number. So here we have Is multiplied by e raised to negative of a large number. Or we can write Is multiplied by 1 by e raised to the power of a large number. E raised to a large number will be an even larger number. So we can write this is Is divided by a very large number, which can be approximated to 0. That is why in this model we have taken Id to be 0 when Vd is negative. Now let us take the natural logarithm on both sides of this equation. Then we get log of Id is equal to log of Is e raised to Vd by Vt. Now log of A multiplied by B is log of A plus log of B. So here we can write log of Is plus log of e raised to Vd by Vt. Log of e raised to Vd by Vt is simply Vd by Vt. Now let's take log of Is to the other side of the equation. Then we get log of Id minus log of Is is equal to Vd divided by Vt. Again, log of A minus log of B is log of A divided by B. So here we can write log of Id divided by Is is Vd divided by Vt. From here we can write an expression for the applied voltage Vd. It is Vt multiplied by log of Id by Is. Let us take an example. Here we have a circuit that has a diode in it. We are going to use the exponential model of diode. We also have a resistor of resistance R, and the current flowing through the circuit is Ix. Positive terminal is connected to this end of the resistance, so we'll have positive polarity here, negative polarity here. If you take a look at the diode, this end is connected to the negative terminal, so here it will get negative polarity, here it will get positive polarity. If you start from here and go clockwise, on the cell you're going from negative to positive, But for the resistor, it is from positive to negative. For the diode also from positive to negative. So we can say the potential drop across R and D have opposite polarity with respect to the applied voltage. Let us now apply Kirchhoff's voltage law. According to this, sum of all the voltage drops will be equal to 0. So here we can write V plus the potential drop across R will be minus IXR plus the potential drop across the diode, which is minus VD, is equal to 0. Or we can simply write V minus IXR minus VD is equal to 0. Here we are taking the exponential model for the diode. So we can write V minus IXR minus, for VD we will write VT log of the current flowing through it Ix divided by saturation current. This is equal to 0. Now we will solve this equation to find whatever is to be found. Let's go to the next model. It is the constant voltage model. Before we get into that, let us take a resistor and apply a voltage across it. Resistance of my resistor is R and the applied voltage is Vx. Let's take the current flowing through it to be Ix. Now, if I plot the relationship between the current and voltage in this circuit on a graph, taking Ix on the y-axis and Vx on the x-axis, this is how it will look like. Here I have taken the current in the y-axis and the voltage in the x-axis. So if I take the slope of the graph, it will be Ix divided by Vx, which is 1 by the resistance. Keep this in mind when I show you the relationship between current flowing through a diode and the voltage applied across it in the constant voltage model. This is how it looks like. Until the applied voltage becomes a particular value, the slope of the graph is 0. After that, it suddenly becomes infinite. Slope of the IV graph is 1 by R. So initially we could say 1 by R is equal to 0, or R tends to be infinite. When the slope becomes infinite, we can say 1 by R is infinite, or R is equal to 0. Let us take our diode. Here the resistance is really high and the current is 0. So we can model it to be an open circuit. Because an open circuit does not let any current pass through it, so we can consider it to be having infinite resistance. On the other hand, here we have R equal to 0 and I is infinite. In that case, we can model our diode to be a closed circuit. Here the current is infinite, so the resistance can be taken to be 0. But we made a mistake here. When current becomes infinite, the potential across the diode is not equal to 0. Let us call it V0. V0 is the applied voltage at which the diode switches on. To acknowledge that, in the model we can also put a cell of potential V0. When the applied voltage V is less than V0, we can model the diode to be an open circuit. When the applied voltage V is greater than V0, we can model the diode as a closed circuit along with a cell of potential V0. Let's take an example. I have taken the same circuit from the previous example. We have a resistance R. It is in series with the diode D. Potential applied is V and the current in the circuit is Ix. Here we are going to use the constant voltage model of the diode. Here the diode will get negative potential here and positive potential here, but still we know in this model for the diode to switch on, it at least needs V0 across it. Let us assume that it is the case. Assume that the diode is on. In that case, we can redraw the same circuit like this. I replace the diode with a cell of potential V0. Let us again apply KVL. V minus IXR minus V0 will be equal to 0. This equation is simpler than the equation we got in the previous example when we took the exponential model of the diode. We can solve it to find whatever is to be found. The constant voltage model is obviously less accurate than the exponential model. But for most of the circuits, this much accuracy will be enough for us. There is one simple concept I want to add over here. When we take the model of the diode when it is in forward bias, the P side of the diode will correspond to the positive terminal of the cell and the N side will correspond to the negative terminal of the cell. The next model is ideal diode model. Here the only difference from the previous model is that the voltage at which the diode switches on is now 0. Let's take the diode. When applied voltage is less than 0, the current is 0, so the resistance is infinite. We can model it as an open circuit. When the applied voltage is greater than 0, current is infinite, so the resistance is 0, which means we can model the diode as a closed circuit. Also, when this happens, the voltage across the diode is 0, so we don't really have to add any cell over here. This means for positive voltages, the diode acts as a closed circuit, and for negative voltages, it acts as an open circuit. We could say it passes positive voltages and blocks negative voltages. Let's take the same example again. Here the diode gets positive potential here and negative potential here. Since we are taking the ideal diode model, the moment the diode has some positive voltage across it, we can assume the diode is forward biased and it will act as a closed circuit. So we can redraw the circuit like this. I replace the diode by a closed circuit. Again, by applying KVL, we can write V minus Ix R is equal to 0. Here the equation has become even simpler, but obviously the accuracy has also become lower. Now let us learn about a special purpose PN junction diode. It is called Zener Diode. This is the circuit symbol of a Zener diode. The relation between the voltage applied across the Zener diode and the current flowing through it can be shown like this. You can see in the forward bias, it looks exactly like a normal diode. Once the threshold voltage is reached, the current increases exponentially. Now, assume that this is the characteristics of a normal diode. It has a breakdown at this much voltage. But a Zener diode can have a breakdown at a smaller voltage as well. We call it the Zener voltage, denoted by Vz. This breakdown is called avalanche breakdown and this breakdown is called Zener breakdown. Now, Zener breakdown is exclusive for Zener diodes, but avalanche breakdown is not exclusive for the normal PN junction diode. Even Zener diode can also have avalanche breakdown at this voltage. Let us see how Zener diode is different from a normal PN junction diode. The first thing is, Zener diode has a narrower depletion region because it is heavily doped. Because of this, it has a lower breakdown voltage, which we can see over here. It is also designed to operate safely in the reverse breakdown region without any damage. In the graph, you can see when the applied voltage is Vz, the current increases sharply. Or you can say even when the current increases and take any value, voltage across the Zener diode is Vz. It is constant. So in reverse breakdown region, voltage across the Zener diode is kept constant even when the current increases. Let us see how we can model a Zener diode in a circuit. The first one is the constant voltage model. When the applied voltage is greater than 0, this exactly looks like the constant voltage model of a normal PN junction diode. When the applied voltage is greater than V0, current becomes infinite, resistance becomes 0, and we can model it to be a closed circuit with a potential V0 across it. Let's take our Zener diode. When the applied voltage is greater than V0, we can model it like this. Now, when the applied voltage is negative, current is 0 for some time, but when it reaches the Zener voltage, we have a breakdown. But the Zener diode is designed to operate safely in the breakdown region. It will not get damaged. Instead, we'll get an infinite current in the opposite direction, and the potential across the diode will be constantly Vz. Since the current is infinite, resistance will be 0. So we can model it as a closed circuit with a voltage Vz across it. One important thing to note here is this happens when the Zener diode is reverse biased. Vz is a negative voltage. So when I model the diode, I took the negative terminal of the cell corresponding to the P side of the diode, and the positive terminal corresponds to the N side of the diode. Now, this happens when V is greater than V naught. This happens when V is less than Vz. What happens when V is between Vz and V naught? In the graph, we can see the slope is 0. That means current is 0 or resistance is infinite. So between Vz and V naught, we can model the diode like this. It is an open circuit, so that gives us infinite resistance and 0 current. Now let's take the ideal diode model. The only difference we can see is in the forward bias region, the diode will switch on at 0 voltage. It doesn't need V naught anymore. Therefore, when the applied voltage is greater than 0, we can model it like this. Current is infinite, so resistance is 0, which means we get a closed circuit. Also, when this happens, the voltage across the diode is 0, so we don't need any cell over here. When the applied voltage is less than Vz, the model will look exactly like the constant voltage model. Current becomes infinite, so resistance is 0, which means we have a closed circuit. While this happens, the voltage across the diode is Vz, which is negative. So we have Vz applied over here, but with negative terminal here and positive terminal here. Between Vz and 0, we have 0 slope, which means 0 current and infinite resistance. So we can model it to be an open circuit. Let's take an example. We have a circuit with a normal diode over here and a Zener diode over here. These are both silicon based diodes and the Zener voltage is 20 volt. Input is given over here and output is taken across the resistor that is connected parallelly to our Zener diode. You can see the input waveform over here. It is one cycle of a sine wave and its peak voltage is 60 volt. The first half cycle is positive. So we get positive potential here and negative potential here. The normal diode gets negative potential here and positive potential here, so it will be forward biased. I am going to consider the ideal diode model, so we can model this to be a closed circuit. Again, since we are taking positive potential here and negative potential here, the Zener diode will get positive here and negative here, which means it is reverse biased. But we know even if the Zener diode is reverse biased, as long as the negative potential across it is less than the Zener voltage, it will not start conducting. Zener voltage here is 20 volt. So, when the applied voltage is between 0 volt to 20 volt, we can model the Zener diode to be an open circuit. Let us draw the modified circuit when the applied voltage is between 0 and 20 volts. The normal diode is modeled as a closed circuit. Zener diode is modeled as an open circuit. Now, here the input is directly applied across the resistor. And we are taking the output across the same resistor, which means the output is going to be exactly the same as the input. To plot the output, let us take a graph. For reference, I have kept the input waveform also. When applied voltage is between 0 and 20, output is exactly the same. So we can plot it on the graph like this. Now let's see what happens when the input voltage is between 20 and 60 over here. Voltage is still positive, so we get positive potential here and negative potential here. Since the normal diode is getting negative here and positive here, it will again act as a closed circuit. Zener diode is getting positive here and negative here. It is reverse biased. Also, the potential across it is greater than 20. So it is in the breakdown region. It will act as a closed circuit with a potential 20 volt across it. Now, when V input is between 60 volt over here and 20 volt over here, again the voltage is positive. So we get positive potential here, negative potential here. Negative here, positive here will make the normal diode forward biased and it will act as a closed circuit. Positive here and negative here will make the Zener diode in the reverse region, not just reverse region, The potential is between 60 and 20, which means it is in the reverse breakdown region. It will act as a closed circuit with 20 volt across it. So we can say from 20 here to 20 here, the model will be the same. For V greater than 20, this is how the circuit model will look like. Note that I have taken the positive terminal of the cell where the N side of the Zener diode is. I've taken the negative terminal of the cell where the P side of the Zener diode is, because this is happening when the Zener diode is in the reverse breakdown region. Now we have a 20 volt here and the output is taken exactly across it. So whatever is the input, output is going to be 20 volt. We can plot it in the graph like this. Now, when the input voltage is between 20 over here and 0 over here, again it is positive, so we get positive here and negative here. Normal diode will be forward biased and an open circuit. Zener diode will be reverse biased, but voltage is not enough for a breakdown, so it can be modeled as an open circuit. Let's modify the circuit model according to that. Here again the input is directly applied across the resistor and we are taking the output across the same resistor. So the output is going to be exactly the same as the input. Let us plot it on the graph. Now in the second half of the cycle, the input voltage is negative. So we get negative potential here and positive potential here. The normal diode gets positive potential here and negative potential here. It will be reverse biased. So we can model it as an open circuit. Zener diode will get negative here and positive here, so it will act as a normal diode in forward bias. That is a closed circuit. Let's modify the circuit model according to that. Normal diode is an open circuit, Zener diode is a closed circuit. One thing is we are taking the output across a closed circuit. There is no potential drop anywhere, so the output is going to be 0. Or you can think like this. This is opened, so no current is going to flow through the circuit. So the output voltage is 0. Let us plot it on the graph like this. Now let us learn the two types of characteristics we can plot for a circuit. I'll take a simple circuit as an example. There is an input Vx, there is a resistor R, and a PN junction diode across which the output is taken. Now, when Vx is positive, we'll get positive potential here and negative potential here. The diode will be reverse biased and we can model it to be an open circuit. The circuit is open, so no current is going to flow through it. I can write the current Ix is equal to 0. Now, when the input is negative, we'll get negative here and positive here. So for the diode, we will get negative here and positive here, which makes it forward biased. I am taking the ideal diode model, so I can model it to be a closed circuit. When Vx is less than 0, we are taking the output across a closed circuit. So output voltage is going to be simply 0. There is a current flowing in the circuit. Using Ohm's law, we can write current Ix is Vx divided by the resistance R. Now, when Vx is greater than 0, we have an open circuit here. So no current is flowing through it, which means no potential drop is there across the resistance R. So whatever is applied here will be exactly seen at the output. So we can write V out is exactly equal to Vx. Again, since the circuit is open, no current is flowing through it. Ix is equal to 0. Now, the first characteristics we are going to plot is the input-output characteristics. It will look like this. We take the input on the x-axis and output on the y-axis. When input is negative, output is 0. When input is positive, output is equal to the input. So the slope of graph over here will be 1. Next, we have to plot the Vi characteristics, and this is how it will look like. When input is negative, we found Ix is Vx by R. Ix is proportional to Vx and the constant of proportionality is 1 by R. So we'll get a straight line with slope 1 by R. Now when Vx is positive, Ix is simply 0 and that is what is plotted over here. So that's all about it for today. See you in the next video. And don't forget to subscribe.